So, so this is example number 2 on failure theories for brittle materials. Let's consider the same bracket that we were using in our previous example for ductile materials, but this time we're going to change the material property to a uh, a grade 30 cast iron property. Okay, and what we want to do is same as before. We want to find the force, and we want to maintain a factor safety or a design factor 1.5. And again, we are looking at this particular location. And one thing that you can see from this particular location is that your big D is 1.5. That's the big D here. And then the reduced D is 1.0. And then your radius is 0.125 inches. So this is given from the geometry itself, and we know those values. Okay. Now, for this to be safe, as was before, we will have to make sure that this is actually bigger or equal than 1. And to find the material properties, we go to the your table A24, and that table for grade 30, you can see I get the values right here. So your ultimate tensile is equal to 31 KSI. Your ultimate in compressive strength is 109 KSI. So that's given in the problem. And we know that in the problem, this particular problem, we are going to need your stress concentration factors because we are working with brittle materials. So let's go ahead and do that first before we keep moving on. So we know that R over D is actually equal to 1.25. Your big D over small d is equal to 1.5. So then in the problem you do is, this is this value right here. This is 1.5. So the value that we are working with is right here. We intersect this curve right there, and then we more or less come here. You eyeball all these answers. This is 1.6. This is about 1.7. So I can say KTA is almost equal to 1.79. Now, for the area, if I want to use my sigma XX, what you have to be careful here is that is your load F divided by area. And the area that we are using is this area, is the smaller diameter. Okay, so all the tables actually give you that information. Okay, so we go now for the case for torsion. That's the next table. We do the same thing. R over D is 0.25. So this is 2. So this is 1.3, somewhere in between there. So the value is somewhere there. Okay, so this is 1.2, 1.3. So what we could say, this is, again, eyeballing this answer is 1.38. And what you can see here is, yes, this is exactly the same as we always use. This is torque over Q. Note that Q is equal to J over C, but you have to use small d. You see, not the big D, your small d. So that will give you pi d cubed over 16, what we have been using for the small d, never for the big D. So we move on for the next case, okay, for the moment. For the case for the moment is this value right here, 0.25, 125, and intersects this curve, and you come over here and you get almost this value. So the value that I'm getting, this is approximately, this I'm eyeballing this answer is 1.56. Okay, and then your value of your stress that you're going to be using here is M over Z, and note I'm using this small value, where your Z is equal to pi d cubed over 32. So you always have to look at the table and know what your Z's are, okay? Okay, So with that said, now we can move on, and this actually is identically the same problem as we did for the case of the previous case. So you have to do a free body diagram at that particular location, okay? And you find that Vy is equal to minus F, Mxx is equal to 15F, Mzz is equal to minus 14F, and for a design factor 1.5, as we did before, we find that the value I get is, so you find these are the values I got from my previous example. Okay, so, and again, this stress goes in this direction, this stress goes in this direction. Um, this is tau xz, this is sigma xx, and we are working in the, change the colors here quick. We are working the x direction. This is the y direction. This is the z direction. Okay? So your state of stress then will be equal to sigma xx 0, tau xz 0, 0, 0, 0, 0, tau xz, okay? Where you have sigma xxb will be equal to mzz over z, and we already talked about that in the previous slides. Now, what you have to keep in mind in these problems is, now we are working in brittle materials. In brittle materials, it is important to give the stress intensity stress concentration factors. We cannot eliminate that. In general, we would have this extra term, right? Plus KTA NXX divided by area. But in our problem, we did not have any axial load, so therefore this went to 0. But in general, you would have that. Okay? So now we can proceed to do this problem. And from the tables itself, we know, we already know that the values that I'm going to work with, KTB is equal to 1.56. KTS is equal to 1.38. And if I plug in all the numbers, and we're going to run the MATLAB code in a minute, and what we find is your loads actually, your stresses actually look like this. 0, and I'm rounding up numbers here for the sake of this discussion. And as it was before, this is all a function of f. But if I want to use your code, I can just say, you know what? I can take this f from here, okay? And I can bring my f outside here. It's the same thing. So all my answers now I can multiply by my letter f, okay? So with this said, what I really need from the problem, I need my sigma 1, I need sigma 2, and I need sigma 3. I don't need my tau. It's not needed for these problems. Okay, so let's run your case. You're going to run this particular case. Make sure that your, yes, it's closed. So you run the code, and we're going to run this in inches. This is KSI. And this is a good example. You enter something wrong, you may have to enter it again. So now the problem is 1.5, and I have loads. Okay, the type of cross section is a circle, and the diameter is the smallest diameter. That's 1 inches. Okay, I didn't have any axial load. My axial, let me look for it here. This was 15. Remember, I'm keeping the f out of the equation. Okay, this is minus 14, and this is minus 1. That's your b. And then this is brittle material. And so this was the values for this problem were 31 and 109. Okay, and the load factors in this problem are, although I don't need it, it is asking, so might as well give the value for axial. And bending is 1.38. And your torsion, oh, I have to start again. Okay, here I am starting the problem again, 1.75. I just got them flipped. So this was 1.56. This was 1.38. Okay, those are the values that we get. We run our code. Remember, the code is going to run for point A and point B. Okay, and let's see the answers that we get. So this is a very, very good example in which you can see that because one side was negative, let me explain to you what's really going on in the problem. So this is really doesn't mean anything, okay? Doesn't mean absolutely nothing because I don't know the value of f. But what's happened is in one case is in compression, right? And the other case is in tension. Okay, so look at the different cases. In one case, when it's in tension, all the right, and my upper point is in tension, I'm getting is bound by this, is bound by S1, but when I am in compression, is bound by this curve right here. So now you have more value available than this. You have to watch out very carefully because many times, although we may think point A or point C, it is the most critical one. Sometimes we have to actually plot and see what the failure mode looks like to decide. In this particular case, what you could see is you look at the values. You see, the load value, these are actually load values. The values are way smaller for point A than they're for point C. So definitely what you can say is point A is my design point, it is my critical point, and those are the values I am going to choose. That's why your code, actually, when you choose your loads, will always give you point A and point C together. Okay, so let's take this and let's see what the answers actually look like. The first case that you're working with is the maximum, let me change the colors, maximum normal stress theory, and it says the following. You can see what your state of stress actually looks like. This is your state of stress, you see? And this was the identical state of stress that we got here. See, that's how I got my state of stress. And you ran the code, and I found those values. Remember, this is in KSI, and those are values that we'll use, not in PSI. Okay? So these are my principal stresses. So let's write them down. So in the problem, before I start, I need to know my principal stresses. The principal stresses are 0.397. I have to add an F to the end. Sigma 2 is 0. Sigma 3 is minus 0.063 F. Okay, so those are the principal stresses that we are working with. And the first case, what it says is the shear stress criterion. You're going to work with one of these four cases. Okay, and so what I did was they're not all positive, as you can see. I have a positive and a negative. So I have this case, one of these two cases. So I have to take the ratio. So I take the ratio in this divided by this. This is 3.52. Take the ratio of absolute value S3 over S1, and I find this as 0.59. You can see this number is bigger. Since this number is bigger, then the problem is compression driven. Since it's compression driven, then I'm going to use this ratio right here. Okay, and the value of this stress, it actually gives you, and this was the same thing as we did before. Okay, if you remember, this is actually giving me SUT divided by as sigma 1. Sorry, sigma 1 has to be bigger or equal than 1. This was in compression. I am so sorry. Compression. No, the case that we use is in tension. Okay, so be bigger than 1. So that particular case, I know this is 31. This is equal to 0.397 F, bigger or equal than 1. And what you really have is this particular value is what your MATLAB code is giving you. So what you're really getting from your MATLAB code is 78.086 divided by F, bigger or equal than 1. Then from here you can say F is less or equal than 78.86. Okay, so this is the first value for the first case study, for the first theory. Let's move on to the second one. So just have to watch out with your with the notes. Just fix this in the code. This was actually swapped. So this is the correct expression. Given that expression, then we just do the corresponding comparisons. So the next theory that we are going to work with is the modified Moore circle. And the modified Moore, basically you do your ratios and you see which case you belong as well, and then you choose the corresponding case. And then you can see that you also get the same value, which is kind of expected from the plot itself, right? So your modified Moore is going to actually equal to it is factor safety SUT sigma 1 bigger or equal than 1. And when you replace all the values, you find 31.397 F bigger or equal than 1, solve for F, and F gives you less or equal than 78.09. Then you can do the same thing. You can run your code, and then the mode. This is a second method that it does for you. This method is way more general, and it's the one that it's like using your. This method is way more general, and it's like using your von Mises stress, equivalent stress, and it's very easy to use. These are the equations used to replace all the values in here, and then at the end of the day, you say what is better: C1, C2, C3, S1, S2, S3. You replace the values, you find the sigma, and if this sigma is bigger than 0, then you just use this equation. If it's less than 0, set to 0, that's infinite, so you cannot really use that approach. One alternative that I recommend, just use this approach then instead. Okay, so that also gives you the same value, which is also expected. Brittle column Moore is the most conservative one, and you can see that when you apply all the values in here, you will get something very small. Okay, so if we just go ahead and summarize all these values in a nice table, this is what we actually get. So let's make a nice table. And so these are the values of F. This is a maximum normal stress theory. This is the modify more. This is column more. And this is maximum 78. 78, this gives you 75. Okay, and you can see that how this is way more conservative. It gives the smallest value, and this is what this problem was really asking for. Now we are going to go ahead and move on to this next problem. It's the same problem, also for a design factor 1.5. And what we want to know is if I use these loads, if my component is going to fail or it's not going to fail. Okay, so to do that, we can actually go ahead and do the same table, and we can add the values to that. Okay, so we can add, so let's just do first for the first one, this is 80, and then the second value was 75. Okay, so let's see if it's safe or not. So in this case, all is above all these loads, so this is actually failed. It failed. It actually failed. So this load really cannot handle anything. In this particular case, well, it is safe. This is safe. This actually failed, if you would, because the real value was 74.7. I rounded up just to have a nice round-up value. This value stays below this value, so I am still safe with this, but I will not be safe in this particular scenario. And the one that we commonly people like to use is this theory right here. Okay, this is the most common and is very popular that we like to use. Now, let's consider a different case. Let's suppose, given the load, given everything, how do I actually find my diameter? Okay, let's suppose I did not know this. This is unknown. Then what you will do in such a case is you're going to run the code with different values of your diameter, okay? So let's say you want your factor safety and you decide what theory you're going to use for the factor safety. And then you say, let's say I'm going to do 1. You run it. Okay, you get 0.9. And then let's suppose you run 1.5. You run it again, you get 1.7. And then we reiterate again, okay, this is when above, so it has to be below. I'm making up these numbers, okay? So that's where it's 1.2, and I get 1.1. Okay, it's not that. So I put 1.15, and I tried this number, and then I realized this is 1.00, and say, okay, you know what? I can go with this number. So then you say, then your optimum weight diameter, the minimum diameter for your problem is 1.15. It's the one that actually gives you the smallest possible weight, and it meets your failure criteria that you're using for your design. Okay, so this is how you will actually do these problems, and this completes example number 2.